Hello, young people. We're going to take our understanding of graphing a little bit further because we're going to talk about how we use graphs. Why do we need them? Why are they so important to us? We're especially going to focus on slopes, lines of best fit, and interpretation of graphs and how we can get more information from a graph. So we're going to start out with slopes and lines of best fit. So when we plot a graph or when we make a graph, we get a plot of points and we have these points. Now, the computer does this so wonderfully because I can do all of it. I can plot the graph, I can make it do it, then I can make it do the line of best fit and come up with information from all of that. You can also do it by hand. That's been done for years and years and years. So I want you to know some features first of all. Here's the title, volume versus temperature. We have axes label, and both of them have units because it's a line graph. I have to have units that I've measured. We go to the scaling. Now you'll notice that this scale starts at 250. It starts at 250 because officially I'm putting little breaker bars here, and I know that that's 0 right there, but I'm starting at 250 because I don't need to start at 0. My graph would be very skewed if I did that. So sometimes I can put breaker bars right here and put a break and start with a number and then continue forward. But I can see this is 20 Kelvin, each of these spaces. Going up, I have 1 milliliter going up. So there's my scale. I've plotted my points, and then finally I've drawn the line of best fit. Now this circled area is the equation of the line in y equals mx plus b format. You guys have heard that. You know what I'm talking about when I say y equals mx plus b format. This is y is equal to m, 0.0169, that's the slope of the line, x plus 0.0091. That is the b portion. That's where the x-axis or it's the y-intercept, or where the x-axis is 0. So there's no x-coordinate, but that is where the y is when x is 0. That's what the y-intercept is talking about. So that's how we get that. If you're doing it by hand, you have to do this by hand and then take the slope of the line in several places and find the y equals mx plus b portion. How would you do that? Well, the slope equation, the first thing we do is we find the slope, the rise over the run. If you're given data points, that's the easiest way to do it. Rise over run, y2 minus y1 over x2 minus x1. We can then take that information and translate it algebraically into y equals mx plus b. Once we find where the x is 0 and it crosses the y-axis, then we know what the b portion is, and now we have the equation of our line. So we can do it by hand. It's just much easier to do on the computer. So this equation was created doing a trend line option in Excel. So I create all my graphs using Excel, and I use the trend line option in Excel 2016. When I do that, I get the equation y is equal to 0.0169x plus 0.0091. That's my equation. And so I know what the slope is. I know where it crosses the y-axis, and it's x is equal to 0. I know all that information. So the r square value that you saw in that diagram earlier is basically relating how closely does that line of best fit really fit this data. The closer it is to 1, the closer it is, not 0.1, 1, I'm sorry, that's a mistake, 1. The closer it is to the number 1, that's 100%, the closer it is to completely true. So that would mean if it's 101, that's 100% fit. We got a 9.9986, that's 99.86% fit. That's a really good fit. Anything above 95 is excellent. 99 above is like outstanding, wonderful stuff. Anything above 90 we accept depending on the data and how it was collected and what kind of data we've collected. But anything less than 90, we have to question whether or not that's a true line of best fit. So you need to make sure that you're checking your R-square values as you're doing trend lines, especially on the computer or on your graphing calculator, to make sure that you're checking all of that out and making sure your lines of best fit are really good lines of best fit. So this data is really, really close to the straight line that was shown on the graph in the first place. So the data actually fits that straight line really, really well. Okay? Interpolation and extrapolation, these are just methods of analyzing more data and gaining information that wasn't necessarily plotted. These two words are really important to understand, and we can understand them by simply looking at the prefixes inter and extra. So polation is just talking about graphing. When we polate, we're talking about graphing something, but inter means within the graph itself, within the data that we plotted. Extra means outside of the data that we plotted. So we already know the meaning of these two words based upon the prefixes given here. So they're really simple. Inter as a prefix means within, extra means outside or more than, and pola is the root word talking about the graph. So if we got pola, we got a graph going on. So putting the pieces together, interpolation means finding values within the data we graphed, inside of it. Extrapolation means finding data values outside the data that we actually physically graphed. Okay, so let's find a value by interpolation. So here we have our graph. So we want to know what the volume is at a temperature of 330 Kelvin. The reason this is interpolation is because 330 Kelvin falls between around 275 and 375. So it falls between that plotted data. Therefore, we're interpolating because 330 is within the plotted data. 330 is right here. If we go up to the line, we can see that we have a value that is between 5 and 6. It's not exactly between 5 and 6, so I would imagine that once we've interpolated, once we've drawn the line up and we've drawn a line across, we get something about 5.6 milliliters. It's a little more than half, but not quite as close to 6 as we would like it to be. And so a good round guess would be 5.6 milliliters. That's interpolation. It's pretty simple, okay? Extrapolation is no different. The difference between extrapolation is I'm looking outside of the data that I've already collected. So 250 Kelvin. 250 Kelvin is outside the data that I plotted between 275 and about 375. That's the data that I plotted. But I'm looking for something around here at 250. And so what I need to do is first extend my straight line so that I have a straight line going through that point. That's a really important factor. Then I'm going to draw that line at 250 and I'm going to see where it goes. And it looks like it's greater than 4 but less than 5, and it's actually less than 4.5. So I'm going to say 4.3 milliliters. That's a pretty good round figure and a good guess. So 4.3 milliliters would be a pretty good guess here. Notice extrapolation, meaning I was outside the data area that I plotted. I had to draw a line to extend my line of best fit to be able to then use that portion of the line to extrapolate the information that I needed. Okay, so direct versus indirect relationships. Direct relationships means that both variables move in the same direction. So when one goes up, the other one's going up. When one goes down, the other one goes down. They always move in the same direction all the time. Okay? So in this, we have a direct relationship. As volume increases, so does temperature. As temperature increases, so does volume. This is what we call a direct relationship. So as one goes up, so does the other. As one goes down, so does the other. That's a direct relationship. So we can see that. Indirect relationships. Indirect relationships do not mean that the variables move together in the same way. As one goes up, the other one does the opposite and goes down. So the data that we see over here to the side is a perfect example of this. We can see that as volume is decreasing, because volume is clearly decreasing, it's going from 100 and something to around 30. But what's happening to pressure as volume decreases? Well, pressure is going from a little bit above 50, about 60 it looks like, to about 200 kilopascals. So this is a relationship that is not the same. As pressure goes up, volume goes down. As volume goes down, pressure goes up. And so we have to remember indirect versus direct. They go opposite if they're indirect. They go the same way if they're direct. Okay, so how do we change an indirect graph to make it more direct? Chemists love doing this because what we like is we like straight lines and we like straight line relationships. So what we tend to do is we change it so we get a straight line relationship. In this case, We took volume versus 1 over pressure. We changed it to the reciprocal of pressure. In other words, we put pressure over 1. And when we do that, we get volume increasing as pressure and as 1 over pressure increases. And this gives us a straight line, whereas the other one was a curve. We love doing this as chemists. As chemists, this is sort of our bread and butter. We do this quite a bit. So just make sure that you understand the difference between indirect and direct, okay? Thank you very much.